So let's talk about charge and about the forces between charges as we introduced it in our class earlier this week. When we have opposite charges are going to repel, and when we have like charges will attract. So in this figure, you can see three different situations. In the first one, you can see a case where there are two red charges, and I've said red is positive. Sometimes red could be negative. But let's say red is positive, and you can see that in case number 1, Q1 and Q2 are both positive, and so the force that you see acting on them is a repelling force. And you can see that by the direction of the arrow that's showing that Q1 is being pushed away to the left, and Q2 is being pushed away to the right by the force that comes about between them. So this F21, if Q2 is the second charge, could be the force that Q2 is exerting on Q1. And in the second case, where the two charges are blue, you can see that they're also both repelling, and that's because they're both negative. So if Q1 is negative and Q2 is negative, then the force again is going to be a repulsive force, which is pushing one to the left and two to the right, or pushing them apart from each other. Then finally, in the third case, here we can see opposite charges. I have a Q1 that's blue, I have a Q2 that's red, so I have a blue negative that's being attracted to a red positive, and here we see the direction of the force arrows are inward. The other thing that we need to know if we want to actually calculate the force is how far apart they are. So just like the force due to gravity, we see that we have two objects that are attracting each other in case 3, or repelling each other in 1 and 2, and the strength of that force is going to depend on how big are these charges and how far away are they. So let's look at Coulomb's law. Coulomb's law is the equation that allows us to calculate the exact strength of the force. Force over here is force due to the electromagnetic attraction or repulsion, Fe, between two charges. And in this equation, we're going to call the charges Q. Q is our variable for charge. So I have Q1 and Q2. Those are the size of my two charges. And then down here, I have my distance. And the distance, just like it was with gravity, is going to be squared. Now, there are a couple of differences here. We have K as our constant, and our K constant is going to be different from the constant that we used when we saw a similar equation for gravity. And then the other thing that's different is the units of charge. So we need to think about what is the unit that represents how big a charge is. And that unit is called a Coulomb. So the Coulomb is a unit of charge, and the Coulomb is a really big quantity of charge. You don't really find charges of 1 Coulomb strength. Coulomb is abbreviated C, and that's how we're going to actually find our Q being measured, Q in coulombs. So this equation tells me that the electrostatic force between 2 point charges is K Q1 Q2 over d squared. Now let's compare this a minute to the equation that we already are familiar with for finding the force due to gravity, because they're exactly the same kind of equation and they're in the same format. So the differences, as we said, are that the first force that we looked at, gravity, Fg, was a force between masses, but now our force due to an electromagnetic attraction or repulsion is going to be dependent on charges. So if you look on the left, we have a force due to EMF, and this is going to be based on the size of Q1 and Q2. On the Q1, you see a large blue charge, and then the Q2, you see a small red charge. So Fe is kq1 q2 over r squared, where r is the distance between the two charges, and just like it was before, that has to be measured in meters. Over here, on the right, when we look at our force due to gravity, it was mass 1 and mass 2 always being attracted to each other, and that was g m1 m2 over r squared, or d squared. So these equations really look just the same. It's going to be the proportionality constant that's quite different between them. K is very different from g. And then the second thing is that when we had mass in kilograms on the gravitational calculation, we now have Q being measured in coulombs in the electromagnetic force calculation. So before we make any calculations using Coulomb's law to find the force between charges, let's make a comparison of the two proportionality constants. The constant big G that we already know from the universal law of gravitation, from F is g m1 m2 over d squared, was really tiny. You remember we used that number a lot, and the multiplier that we used, big G, was 6.67 times 10 to the minus 11th, and then the units, Newton meters squared per kilogram squared. Now remember, that number was so small, if we wrote it out, it came to this, 0.00000000667. So that's a really tiny number, and what it meant was it takes really large masses to be able to generate any significant gravitational force. That's why you don't feel the force due to gravity between you and your car when you're walking up to your car, but you can feel a force due to gravity between you and the Earth, even though that force still is pretty weak. The force between you and the Earth, or your weight, is not that big a force. When we move on from gravity to now looking at the Coulomb's law constant, the proportionality constant there is enormous. It's 9 billion, or 9 times 10 to the 9th. And now the units are Newton meters squared per Coulomb squared, because our unit of charge is the Coulomb instead of the kilogram. So this number, 9 billion, means that even if two charges were just 1 Coulomb and 1 Coulomb, and they were 1 meter apart, the force between them would be 9 billion newtons of force. And if you remember what our weight is, my weight is about 800 newtons, a force of 9 billion newtons would be enormous. So these constants really help us to see that the Coulomb is a large unit of charge, or seen from another perspective, it's a way of seeing that the force due to gravity is really quite weak compared to the strength of the force due to electromagnetic attraction and repulsion. Now this is a great diagram, and one that comes from an animation that we'll put on the Foundation's course blog, so that you can vary the charge and vary the mass between two charged pith balls or two charged objects hanging from a string, and find out how far apart they would be pushed if we put different charges and different masses on them. So let's just look at what we have here for a minute. The two green balls that are hanging down on the strings are being repelled from each other. You can see that. Each one of them is being pushed out and away from the center, and the reason is that they both have a charge on them. That each of them, we could imagine them being charged positive, have a positive charge, and because of that, they're repelling away from this center point and being pushed apart by the electromagnetic force of repulsion. So since they're both repelling, they rise to a certain distance. And what we can measure is we can measure the distance between them, this distance, and this distance is actually from the center of the green to the center of the red, and that distance is listed here as 161 millimeters. Remember, we're going to have to convert these distances into meters, and if I think about that, 161 millimeters is going to be 0.161 meters. So that's my distance apart. How big is the charge? Well, the charge is over here on a slider, over here on the blue, and the slider has been set, you can slide it up and down in the animation, to be 170. So this is how far apart those two green charges will be pushed, how far apart they'll be repelled, if the charge on each of them is 170, and if their mass is 3 grams. Well, we can leave the mass out for now. Later on we can think about the balance between gravity and the electromagnetic force of repulsion that might allow something to levitate, but I can see that with that charge and that mass, the force between them that's pushing them apart has been calculated here as 10 millinewtons, or 10 times 10 to the minus third newtons. So that's the force at this distance. A distance of 161 millimeters creates a force of 10 millinewtons when the charge on each of them is 170 nanocoulombs. One of the things that you're hearing is that we're getting back to our use of the metric prefixes so that our units are being modified once again by prefixes that are going to change the powers of 10. So what is 170 nanocoulombs? 170 nanocoulombs is 170 NC, little n nano, and that means 170 times 10 to the minus 9th coulombs. That's what nano is. So we know we have really tiny charges on these two green charged objects. Even so, we generate a force of 10 millinewtons between them. So now let's actually work with making the calculation using Coulomb's law and the values of the two green charged balls in the previous slide, and have a look at what that gives us for a force. The force was already calculated. In that animation it showed us 10 millinewtons, but I want to see how we get that. First, I'm going to point out that when I do these calculations, I always simply make a spreadsheet, and I make a spreadsheet so that I can actually put the values in and have the spreadsheet make the calculation for me. Coulomb's constant is here in blue. That's the K value, and K is 9 times 10 to the 9th. In fact, it's always 9 times 10 to the 9th, Newton meter squared per Coulomb squared. So when I put that value in my spreadsheet, I can just leave it there for all calculations. Then I make a box for Q1 and a box for Q2, the first charge and the second charge. And in this case, they're both the same. They're 1.70 times 10 to the minus 7th coulombs. Let's see what that comes from. You remember our slider said 170 nanocoulombs, and I know that means 170 times 10 to the minus 9th coulombs. But if I fix the scientific notation, so there's just one digit and then the decimal, the way scientific notation is generally written, I'll see that 170 times 10 to the minus 9th is the same as 1.7 times 10 to the minus 7th coulombs. And that's something we did in our scientific notation work. Our spreadsheet will do that automatically. So if I enter the value down here in the spreadsheet, 170 e minus 9, it'll correct it and make it 1.70 e to the minus 7th, and it'll do that work for me. So there's my first charge, and here's my second charge, and they're the same. These two charges are identical. The last thing I need here is I need the distance, and the distance between them, notice, is 0.161 meters. That came from knowing 161 millimeters was listed as the distance, so the distance is 161 millimeters, which is the same as 0.161 meters. So I have that value over here for the distance, and now I have all my values in. Now the great thing about the spreadsheet is I can make an equation in a box in the spreadsheet that will use the charges that I've put in and the distance between them, and it'll simply make that calculation. Then we'll see how the same thing is done if we wanted to do it with the long form of the equation in a calculator. Down here in my spreadsheet, where it says force is kq1 q2 over d squared, I'm going to take this box where it says force, and I'm going to make an Excel formula that says equals, and then I would say this times this times this divided by this squared, and then I'll say enter, and this spreadsheet cell will make the calculation for me. If you want to learn how to do that, you can see me and I'll show you how to make your own spreadsheet that can do homework problems with the Coulomb's law. But we also know we're going to need to know how to do this with our calculator and use Coulomb's law the same way we use the universal law of gravitation. So let's rewrite Coulomb's law now, and let's put it up here, F equals kq1 q2 over d squared. Now once I've written that, I know what my values are. I know my value for K. It's always the same. It's 9 times 10 to the 9th Newton meter squared per Coulomb squared. Newton meter squared per Coulomb squared. So I have that value, and I know both charges are the same. So now I could say Q1 equals Q2. They're the same, and both of those equal, in this case, 170 times 10 to the minus 9th coulombs. Now, that's the same thing as 1.7 times 10 to the minus 7th coulombs, and either one of those numbers will work on my calculator, even though 1.7 times 10 to the minus 7th is the correct scientific notation. Finally, my distance. I know my distance in meters, can't put it in millimeters. In meters, 0.161, or if I want to add another place, 1612 meters. So I'm all set. Now I can make my calculation. So my force equals K, 9.0 times 10 to the 9th. Get that decimal point in there. 9.0 times 10 to the 9th Newton meter squared per Coulomb squared times, let's make a little room for this, erase some of this stuff, times my Q1 and my Q2. Since they're the same, I'm just going to go ahead and say times Q1 and Q2, 1.7 times 10 to the minus 7th coulombs times 1.7 times 10 to the minus 7th coulombs. Again, that's Q1 and Q2. All of this is getting divided by 0.161 meters. And then I got to remember to square that. That quantity has to be squared before the division. When I do all this on my calculator, I'm going to get a total value of 0. If we look at it, 01009. Well, 01009 is the same as 1.009 times 10 to the minus 2 newtons. And that would be a correct answer. It's also correct to call it 10.01 times 10 to the minus third, or 10 millinewtons. So that's what's been done. In the simulation and animation before, it showed the force as 10 millinewtons. 10 millinewtons is the same as 1.009 times 10 to the minus 2 newtons. So here's a classic Coulomb's law setup, which in fact has 4 different charges instead of just 2, charges A, B, C, and D. And they're all in a straight line, and all of them are exerting a force on each other. A and B are both positive, so they're repelling each other. We see that B and D would also be repelling each other, but that pushes B to the left and D to the right. B and C are attracting each other, C and D are attracting each other. So we have a whole lot of different forces that are going on simultaneously here. And very soon we'll learn to calculate multiple forces and then just do the addition and subtraction for the net force. But for right now, let's just focus on A and B, or B and D. So my Coulomb's law tells me that the force between A and B, F, A, B, due to the electrostatic repulsion, is going to be K times QA times QB divided by the distance between AB squared. And in doing this calculation, I have to look at 2 different prefixes. My charges on A and B are in millicoulombs. 5 millicoulombs for A and 3 millicoulombs for B. And then my distance is actually not in meters, but micrometers. Distance of 9 micrometers. So to make this calculation, I have to remember that 5 millicoulombs is 5 times 10 to the minus third coulombs, and that 3 millicoulombs is similarly 3 times 10 to the minus third coulombs. If you look at micro, you might remember that micro means a millionth, so the distance that I'm going to put in here is not 9, but it's going to be 9 times 10 to the minus 6th meters, and that's what a micrometer means. So if I put these values in, and I make a calculation, I should be able to find what FAB is. So I want you to do that. I want you to make that calculation and come up with a force. Find out what is the force between positive A and positive B if A is 5 millicoulombs, B is 3 millicoulombs, and the distance between them is 9 micrometers. You've got the K value, you know it. K is 9 times 10 to the 9th. I'm going to write that right up here. K is always 9 times 10 to the 9th. And the units, which allow everything else to cancel, are Newton meter squared per Coulomb squared. After you've done that for A and B, you might try doing the same thing for the force between A and C. Now, to find the force between A and C, you have the A charge, and then you have a negative charge on C, which is minus 2 millicoulombs. And the distance between them means you've got to add up the AB distance and the BC distance, 9 and 8, so that'll be 17 micrometers. So try those problems. Try those as part of our homework. You've got all of these great guides that show you how to do it. There's another video that's on the blog that you can check out also, and you have the reading to help support this thinking. But make that calculation for homework, FAB, and then try on your own F between A and C. Okay, good luck.